Hello, everyone, and welcome to the last Stellar Developer meeting this year. And on the agenda for today, we have two things. We have Jay from the core engineering team. They'll talk about some new additions in Protocol 22, and then he is going to give some demos. So I will invite Jay to join me here on stage.
Hello.
Welcome,
Can you hear me?
Yeah, I can hear you.
Okay, great. Hi everyone. I'm Jay, core developer. Today I'm going to walk you through the building blocks that we introduced in Protocol 22, which went live this month, a couple of weeks ago. Specifically around the graphic primitives, namely the BLS12381. So the cap for BLS12381 is cap 59, which was introduced, I would say 3 or 4 months ago. But today I'm going to focus on just like a high-level overview of what you can do with different types of functions introduced, as well as the SDK interface. And I'm also going to show a couple examples, simple ones, to illustrate how you can make use of these core functionality today to build useful applications. So let's get started. First, let me share my screen. Okay, so I'll be walking through a few things. So first, just briefly take you through the cap. Since this is not a protocol meeting, I'll just be really brief and not spend any time explaining the details and nuances. You can read more about them. So this cap 59 is about BLS12381. So the BLS12381 is a new curve that's added. It's not one curve. It's rather like a family of curves. There's namely the G1, which is the base field, and then the G2, which is the extension field. And what's useful about this curve specifically is that you can compute pairings, which is taking a point in G1, point in G2, pair them, and then it maps into a different point in a higher degree space. So at a high level, why is this useful, you might ask? So just like cryptography, what we wanted to compute, like we want to do computations, and we don't want to do them in a plain manner, right? Just like ECDSA, you utilize the properties of elliptic curve, and then particularly the discrete logarithmic problem is hard to solve, meaning that if you multiply a point a certain times on the curve and get a different curve, it's really hard to invert that process to get the number that you multiplied with, which makes it useful for private key and public key. So same principle here. BLS12381 is just an elliptic curve, and it can be used for signatures, which I will show in our first example later on. But it can do a lot more. So the high level gist of this is that using the new curve, you can do encrypted computation that follows certain rules, and these are the basic building blocks which people use to build more advanced and interesting applications such as zk-SNARK. All right, so here are the new host functions introduced. I think the total is like 12, if I remember correctly. There's the basic ones: point addition, G1, point multiplication with a constant, MSM, which is basically a scalar, like a vector multiplication, which is just multiplying a vector of number by a vector of points and then add them up. So these ones, the hash to curve and map to curve, these ones are if you want to use a digital signature scheme, like if you want to map a random message onto the curve and map to a point and perform the cryptographic functions on it, you first have to take that message and you have to hash it onto the curve. Internally, how it works, very briefly, is that there's hash function SHA-256, and then you also provide something called a DST, which is the domain separation tag, which is just a tag that you append to every message, such that your application's domain is separate from, say, like Ethereum's application. So it's always good to have a unique DST for every application to avoid some kind of intricate attack. So basically how it works is that it just hashes, repeatedly hashes that message into a certain length, which corresponds to the length of the point on the curve, and then it checks if that point is on the curve, and then if not, it add one and repeat, and then once it is on the curve, then it multiplies by some cofactor to send this curve to the correct subgroup. So this is just getting a little bit into more detail, that these curves, obviously they are prime, they're prime field. So the numbers on this curve are modulus of a large prime. In this case, the prime number is 381 bits long, thus the name BRS12381. And the subgroup is different. Subgroup is the number of points that we pick, or the definition of the curve pick, such that these operations are defined. So the subgroup is a subset of all available points on the BRS12381 curve. And then for this particular case, the subgroup size is 256 bit, so which is very convenient to be represented as a big uint 256. And so some of the host functions here actually, if you look at, they are called FR, which basically takes some U256 vowels and then add them together. These numbers represent the scalar in the definition of this particular curve, where the modulus of the scalar equals the subgroup size. So this is useful for manipulating the points, multiplying them and then making sure that this scalar is actually represented by the points on the curve. So we just covered hash to curve, and then then we repeat for G2, which is different group of points. Same thing here, map to G2, hash to G2. And then the important one, or I guess the most interesting one that the applications build off of is the pairing. So what the pairing does is, I'm going to borrow some other slides here. So this is just a one-page explanation for BL signature, which we'll cover in a bit in our example. And here is just the definition of a pairing, which takes a point in the first group, point on the second group, pair them up, and send it to a different group. The interesting about the pairing is that it is bilinear, which means that it is linear with respect to both the first term as well as the second term. So here you see pairing of P plus S is equal to pairing of P times pairing of S. And same here on the second term, Q plus R, you can pair them separately and multiply together. So the reason here is a multiplication. Again, this is just some details, is that because the pairing result is sent to like a higher degree, the 12th degree. That's part of the name BRS12. So we need to get to the 12th degree extension field, which is a multiplicative group, which means you can perform like multiplications instead of an additive group, which is our G1 and G2. So just some details, but the important fact is that you can these relationships can hold, and then by the extension of it, if you have a on the left side, if you have a P repeated 8 times, this is essentially multiplying the result 8 times, and then which is equivalent to taking the this pairing result, the plane pairing result of P and Q, and take the exponent of A, and then you can move this A either on the left side or on the right side, or move it out. It doesn't matter. So the pairing, this pairing relationship can be quite useful, as we'll see in the example of both signature as well as a SNARK verification. Okay, so I think that goes over, well, we just covered the FR, which is the field. This is just a very simple like modulo arithmetics, but with a very specific modulo, like addition, subtraction, multiplication, power, inversion, and that's all. So now let's look at the SDK. So how does this look inside the SDK, which is what you'll be interfacing with? So if you look at the SDK, it sits inside the crypto library, and then there's a BRS12381 module. So all of the functions are exposed inside the BRS12381 module. So the few additional functions like checking if a point is in the subgroup, but overall there is a pretty much one-to-one correspondence between the host function and the SDK function. Oh, and also one thing interesting to notice is there's a 2 addition method. One is just a plain addition, and then the other one is the checked addition. So the reason for that is, so remember what I said earlier was the BRS12381 points are defined over a particular subgroup, but just the addition operation can perform on any point on the curve, doesn't have to belong to the subgroup. But in order for that addition to be useful for our pairings and for our other like a SNARK operation, like they have to be in the subgroup. But the subgroup check is kind of expensive. So if you have a contract which does like a number of these additions, and only you want to make sure the end result is on the subgroup, then you can use the plain add function, which is not taking which is not taking the check. It's just doing the addition. Whereas if you wanted to be safe, and then you wanted to use the checked add, which performs the subgroup check in the end. Multiplication, these are all very standard. Repeat for G2. Pairing check. Oh yeah, okay. One thing about the pairing check here, like I mentioned earlier, in this equation, this is a pairing check. It's checking a pairing of 2 points equals some relationship of pairing, like with either like a result of a pairing multiplied by each other, or like additional terms. But the pairing result itself is a point on a higher degree in a higher degree extension, F12, and then to compute that F12 is very expensive. So the parent check is intended such that we can perform multiple pairings together, and then check that the end result equals to 1, which means this pairing returns true or false. If it satisfies true, otherwise it's false. The benefit of that is that these intermediate results, they can be performed on a much lower degree, which is much more efficient. And only at the very end do you have to, or you don't have to do it, but like internally the algorithm will send that to the 12th order and then do the comparison check with the number 1 in 12th extension. So the reason for that is in most of the applications, either in signature checking or in snark verification, you only need to do pairing to check certain relation hold. Like in a snark, for example, you are checking that your polynomial contains a certain structure. By that, you are computing some polynomial relations, and then you're checking that the left side equals right hand side. This relation holds. So you in none of the point you actually need that 12th degree extension point. All you have to do is to make sure the left side equals right side. So far I haven't heard of any application that specifically needs the result of the pairing. So that's why we went with this design of just passing a vector of G1, vector of G2, perform pairwise pairing, and then check the result in the end. If it's equal, then equal to 1, then return true, otherwise return false. So it's just it's underlying math is the same, but just something to be aware. Like it's not taking a single point pair with a single point, but taking a vector of pair with a vector. And then these ones we covered. Okay, so I think that's it for the building block. Oh, it took 20 minutes. Should probably speed it up a little. Huh? Okay, so let's talk about the useful applications. First of all, the BLS signatures. So I think I went through this in one of the protocol meeting earlier, so I'll just keep it a little more brief because the other ones I think more interesting. So the BL signature, the way it works, I'm trying to find the paragraph here that does the explanation. So yeah, so here there's some kind of secret key, and then sorry, this is a public key. What does it explain? Okay, so the public key is some number times the point, the generator point, and then the signature is the public key times the hash of the message. And by the pairing property, if you do the public key and the hash of the message, and then you move the scalar part around, in the end you'll get a check, which is the generator. So the pairing of the public key and the hash of message equals the pairing of the generator and then the signature. So yeah, it's fairly straightforward. The public key here, sorry, I don't know why it's called PK. It's actually just a secret key here. You can move it. It appears on the left in the beginning, but you can move it on the right, and then this becomes the signature. So the left and right must hold if the signature is valid. And the good thing about it is that if you have the same message and then multiple public keys signing the message, then you can essentially just aggregate all the signatures together and aggregate all the public keys together, do this off-chain, and all you have to do is just to verify one pairing. Then you can verify potentially hundreds of signatures all at once. And this is if the messages are same, but if the message are unique, then for every message, like m number of message, there will be like m+1 pairing checks. So that's the general idea of the PRS signature. So let's see the example So we have here. Hope you can see the code here. So this one example is already in the Solarbound example repo. You can look at it today. I try to keep it documented. I think it's fairly straightforward. It's pretty much just an increment contract, but the increment is requires an auth, which is for every time you increment, it will check called check auth, and then check some the signature payload and then the public key. So inside here is basically just loading the aggregate public key, loading your domain separation tag, and then construct the vector and call pairing. And that's all that is. And then you can look at the test, which is doing most of the setups. Here it contains 10 pairs of signatures, applying the aggregation and signature aggregation. And then here just runs the test, which invokes check auth with some random payload. If I run that, yeah, the signature passes, and then it dumps out the budget. And then, yeah, so this simple operation is like 31 million CPU instructions. So yeah, remember this is 10 different signatures on the same payload. So 31 million to verify 10 signature. You can do also more if they are more. So that's a very brief walkthrough of the VRS signature. So now I want to go and do something new and potentially more interesting, which is the GROS16 verifier. So in order to show that we have the building block to build real ZK applications, I went and generate a very simple proof, and then used a very simple implementation of the GROS16 verifier to verify that proof. And I want to walk you through it. So I don't know if we have enough time for me to actually. So do we have time? How much time do we have?
Yeah. Take the time you need. Yeah.
Okay. Yeah, because I do want to just walk you through the steps that's required to generate the proof and see it in action. Because a lot of these is it looks like magic when you first run it, like just dump a bunch of things. So okay, so here don't know if you can see the link here, but I'm basically using circom.io. If you just search for it as the installation, the getting started guide. So circom is a tool. So circom and SnarkJS is a pair of tools. One is for defining the circuit, which is a arithmetic relation of what you're trying to compute. And then SnarkJS is a tool that allows you to take in the circuit and do all kinds of computations and generate the proofs and also verify the proof. So what we're doing is we're going to just follow this exact guide here, define the circuit, do all the setup necessary, generate the proof. And then once we have the proof, we will write our own contract to verify it in Solarbound instead of verify it in SnarkJS. Okay, so let's see. Okay, I'm going to make this split screen. All right, hope you can see both of my screens. So I did a little bit of preparation. So here's a brand new folder. I have these two files. These are the exact instructions here. It tells you to copy the input, copy the circum I just did in advance, so we don't have to go through that. So the first thing it wants you to do is to install these dependencies, which I already did, so we can skip that. And the second one is that it tells you to define the circuit in the circump language. The circuit is really simple. It's the simplest you can get. Basically, multiplying two numbers and then output the result of the multiplication. However, the interesting part is that these inputs A and B are private inputs. So in the end, your proof will prove that this computation was done correctly without revealing what A and B is. So only the only public output will be C, the number, the result of the multiplication. So what we did here is just copy this exact program into this multiplier file. And then the next one, compiling the circuit. So yeah, so here gives you the circuit instructions, how to do that. So this is basically just writing this circuit in some formats and so that it can be understood by the other tools. But there's one thing we have to change on this command, which is BRS12381. So the reason that we need to specify this is the circuit compilation needs to know the range of the range of prime numbers. So it needs to take the prime number, the 381 bit number associated with our curve, right? This BRS12381, and use that as a curve to generate this circuit. Otherwise, I don't know what happens. Although I haven't tried, but you should do that. So once you do that, it will generate the multiplier in this R1CS format and then some other stuff. So the R1CS is a rank 1 constraint system. Why is it called? So think of any complex computation like A squares times B equals C, something like that. You can always break it down into simpler computation by creating intermediate gates and then assigning intermediate gates to more intermediate, and then like in the end you just compute two things to an output. So the process of R1CS is just deconstruct a complex computation into something simple, that the left-hand side times the right-hand side equals an output, whereas both left-hand side, right-hand side, and output are rank 1, which means the highest polynomial degree is 1. So you can have like A plus B, but not A squared. So that's what it is. Okay, once you do that, the next step is to compute the witness. So at this point, we have the circuit, which is our structure of our computation. But in order to compute it, like in order to be verifiable, we have to compute it with some inputs and then generate the proofs and all that. So here it's just defining the input. So I did it here, which is exactly what it's using. So it takes 3 times 11, so the output would be 33. But we won't know about the 3 and 11. So once we have that, we will enter the JS library. Okay, it's empty right now. It's generated, yeah, some auto generated code to compute stuff. So what we do here is exactly copy this one, but our input is some. Okay, so this one is just generating the witnesses. And then you can also do this with C++. And then once you do that, you have the witness file. I don't think we can load it yet, but it's just a yeah, the witness is just the input basically. Like I think the witness, is it private or just probably? I forgot the exact terminology, but it's possible that the witness is just a public output. So only the C part 33 is contained in the witness. Okay, now comes to the proving part. So yeah, so here there's a bunch of commands. If you do it for the first time, it will look fairly weird because it's telling you to generate a power of tau ceremony. So what it really is so in order to compute the proof. So okay, so remember we have the R1CS file, and then the R1CS is just a system of equations of different nodes, and then every equation is just a simple rank one left right equals output multiplication, and so the next step in order to make that into some kind of provable structure is to convert this into a QAP, which is a quadratic arithmetic program. What it does is to, on each side, the left, right, and output, it fits a number of polynomials that evaluate to at certain points. So the number of equations is the number of constraints, and at each constraint, the polynomial will evaluate at the different points, so to keep them separate. And then the polynomial is an aggregation of smaller polynomials defined over each unique node. So what you think in the end is just instead of left times right equals output, you have a left side polynomial of some degree which matches the number of constraints, and same for right hand side and the output side, and in order to verify this polynomial computed correctly, here's a key concept is in order to verify the computational polynomial, all you have to do is to verify the computation of a polynomial at a single random point. So this may sound a little, counterintuitive in the beginning, but if you have polynomial of degree 2, then there can be only 2 roots, and then if you have 2 polynomial of degree 2, you subtract them together, it can still only have 2 roots. So which means that the 2 polynomial can only be identical at n number of points, where n being the degree of the polynomial. So even if we have hundreds of thousands of constraints in our circuit, the total space of our SNARK, the prime modulus, or rather the subgroup, is 256 bits long. So it is impossible for any collision to happen in real chance. So that's a key concept of how to convert this polynomial into a non-interactive check, which is you just need to make sure that it's evaluated at a truly random value, and then the verifier or anyone can just take the output of that and then make sure and then check the verification that the polynomials equality holds with pairing, what we introduced earlier. So this is what it does. So the power of tau here, the long story short, is just the steps necessary to generate that random point at which the polynomials are evaluated. That's really what it is. So I'm going to speed run through these steps here. It's not really that interesting. There's a lot of outputs. You can look at it later. Yeah. Sorry. BRS 12, 381. That's the first step. Contribute to ceremony. Some random text. So it's going to set up some ceremony, and then the Groq16 requires a universal setup, which is for the whole, like you have to do once, and then a per circuit specific setup. So that's the second step here. So this was the last command. Prepare phase 2, and then yeah, just set up the circuit specific stuff. Okay, and then contribute to the another text. Okay, so now we have the proving key and the verification key set up for this circuit, and the next step is to generate the proof. Okay, so in the end, we have this proof. Yeah, which contains terms which is like encrypted evaluation of polynomial at some point. Then there should also be the public.json. Do we get that? Oh, I think I sent it to the previous folder, but yeah, the public should just have one value here, which is 33. So to verify a proof, so what we need to do is to write a contract. Here it makes really easy for you to do so. There's a step where you can call to generate a Ethereum solidity contract for verifier, and then if we just look at it here, yeah. So the contract itself is it's not that interesting. I'm not familiar too much with Solidity, but most of the logic here is just packing bits into memories, and then in the end, it's called this pairing on a bunch of terms. So we can easily convert that into solid bound, and the output of our contract is just this much. It verifies the proof, takes the verification key, which is some like G1, G2 points, and then a proof which contains also points in G1, G2. Public signal in this case just 1, which is 33 encoded into the scalar field number, and then aggregate the input, and then construct the vector check pairing, and that's really it. And then I copied all of the outputs. It will be a different one than what we generated earlier because there's an entropy. Because of the randomness. But I did this earlier. I just copied all of these the proof part and the verification key part. This is proof, and then this is the VK, and then construct the key, construct the proof, and then just call the verify proof and assert that this result must be true because we've put in the output at 33. So which matches our public output. So let's run this test. Okay, so it's finished. And you can see that this verifying the ZK proof takes around 41 million CPU instructions. It performs 4 parent checks, performs some addition multiplication in G1 space. So if you have more public input, then there will be more multiplication and additions here. But the pairing is there's only 4 pairings, so the total CPU is roughly this amount. Yeah, I think that's it. Sorry for taking longer than expected, but this is it. Hopefully that you can see that this is exciting stuff that you can use to build ZK application today. You may ask, what's the use of it? The real interesting part is in the circuit part. So instead of proving, A, B, and C, you can write a much interesting one, like proving a hash, like computation of a hash, or knowing a path in a Merkle tree, which is like proof of possession or something like that. So all the innovations, a lot of it can happen on the contract side, which is what you guys, are best of. So yeah, really looking forward to seeing what comes out of it. And yeah, let me know if you have questions. We also have a Discord thread. Feel free to post it there, and I'll hand it over to Carsten.
Great, thank you so much. This was really good. I think the examples and walking through the code really made it easier to understand and see potential with. So I know we have one question. Let me see. Elliot was asking a question earlier about if the host functions are all that's needed for CK snarks on Stellar, or if there's still additional functionality that's missing. I don't know if you have an answer for that.
Yeah, to verify the snark, it's all we need. Okay, so there are some quirks in the SDK which we build it like in the like we provide the most generic like interface to expose this functionality, but there's a little bit quirks like for example earlier you see in order to try to store that I have to store the bytes instead of the G1, G2, but that's an easy fix. And also to compute the negation of a point, you have to do it on the contrast side. But yeah, in terms of verification, all the tools are there, but there may be some UX gap which I'm discovering and should be fixing soon. And also with your guys' help, we will be able to make it better. Yeah, but in terms of verification, that's it. But in terms of proving, so as you see, proving has to happen off-chain, and then there's quite elaborate tool set and also like different suites of, there's different frameworks of like Marlin, Gross16, Plonk, and all the other tools that you can use. So we haven't provided any of that, and we don't endorse any of it. I was just using the Snark.js as an example because that's one of the most well known. And then yeah, also the public ceremony aspect. Yeah, we don't have it on chain. So, but yeah, you can verify it, but there's no proving tool chains available at the moment.
Okay, great. Any other questions? Feel free to put them in the chat. I don't think that's the case. We are kind of running out of time, so I will save the walkthrough of quick start for the next meeting. But yeah, if there's no other questions, then I think we will stop it right here. Let's see. Yeah. Okay. Well, thank you, Jay. Thank you for your presentation. It was really good. I think going forward, when we add new functionality in protocol, when we upgrade the network, I think it's relevant to maybe spend some time in these meetings to go over some of the new functionality and some of the things we can do as a developer. So yeah, look forward to more of this kind of presentations. But thank you, Jay, and thank you for everyone who joined. Have a good holiday.
Thank you, guys. Happy holiday.
Bye.